Hi, I'll be reviewing the paper Language Models as Knowledge Bases. In recent years, language models like Elmo, BERT, and GPT-2 have really advanced the state of the art in NLP. Language models have a really simple objective of learning to predict the next word in a sentence. So, for example, if you have a sentence like this, it'll just learn to generate each consecutive word in the sentence. So even though this objective is very simple, it doesn't require any labels. You just need to have a sentence, a sequence of words. And the advantage of this is that you can scale it to just an insane amount of data and use any kind of massive architecture to train the model with. And so models like BERT and Elmo leverage, the entirety of Wikipedia and very large data sets like the book corpus to train this language LM objective on just a huge amount of data. And usually nowadays, the transformer architecture with hundreds of millions of parameters are used to do this. And the interesting thing is that when you scale the language modeling objective to these massive data and massive architecture settings, the gains from scaling them up like this don't seem to be diminishing. So the more data you have and the larger architecture you have, they the model just seems to perform better. And this is unlike a lot of other settings where simply scaling up the data and architecture usually means diminishing gains, not linear gains. And every time we've sort of scaled these models up, Elmo, BERT, and GPT, they've advanced the state of the art in almost every category, from everything from glue benchmarks, which test general language understanding, to question answering, to text generation. So overall, these models are starting to seem more like general language understanding models than just specialized, like a specialized question answering model or a specialized natural language inference model. Instead, they just seem to be able to do everything. And that's sort of the motivation for this paper, which is that if they can do so many things that involve language, maybe we can use them as knowledge bases in that maybe we can query them with subject relation object queries. And, if we query the language model with a pair of subject and relations, it could return an object like a normal knowledge base would. So this paper is essentially asking, can we query these language models for relational data in the same way that we query standard databases or knowledge bases? And this is reasonable to ask because these language models see so much data, like all of Wikipedia and book corpus. And presumably the somewhere in this data a fact, knowledge triple such as Dante was born in Florence was probably seen somewhere in this data. So here, for example, we could query a standard knowledge base with the query Dante born in, and we would get the answer Florence back. The cool thing about the language modeling objective is that just from training the model to do something like Dante then predict born. Just by showing it many sentences of this type, we could potentially query it with this part and have it return this Florence part, which is the answer. So just by virtue of the simple language modeling objective and a huge amount of data, it could potentially infer that Dante was born in Florence. And so in this way, we could query the language model as we would a standard knowledge base. So why would we do this with a language model over a standard knowledge base? Well, the standard knowledge base does have some shortcomings. While it does store these relational data in their exact forms, in order to populate these knowledge bases, we need to actually extract relational data from text or other modalities. And this requires complex NLP pipelines that include entity extraction, coreference resolution, entity linking, relation extraction. So in any of these steps, errors can easily propagate and accumulate throughout the pipeline. So we're not guaranteed that from a piece of free-form text, we'll get perfectly accurate relational data tuples. On the other hand, language models, because we've trained them with so many variations of text, so many different sentences of different style and containing different information, we can query them in a much freer form. So maybe we could query it like Dante was born in, or Dante is a writer from. So language models support these open sets of queries that standard knowledge bases would not. And we don't need to annotate any of this information. We just need to give them hundreds of thousands, hundreds of millions of sentences. We don't need to do any schema engineering. There's actually zero schema engineering. So it's clear that language models have these attractive qualities as potential knowledge bases. But how can we quantify the knowledge that these language models contain? For example, how does the knowledge differ for different types of knowledge, such as facts about entities, common sense, and general question answering? How does their performance without fine-tuning compared to symbolic knowledge bases automatically extracted from text? So this paper aims to answer these two questions. And to do this, they propose the LLaMA, or Language Model Analysis Probe. The idea is that they'll probe the language model like a knowledge base by issuing queries, like we've seen before, like Dante was born in. And the probe inquiries are created from existing knowledge bases of various types. So by using different knowledge sources, we'll be able to test whether the language model knows the information pertaining to that knowledge source. And the probe considers that the pre-trained language model knows a fact if we query it with a subject relation object tuple such as Dante born in Florence. Well, this would not be known. And we turn it into a closed sentence which masks this object out. And then if the language model successfully predicts Florence for this query, Dante was born in, then we will consider this as evidence that the language model actually knows this subject relation object tuple. And they test this probe on multiple knowledge sources. One is the relations between entities stored in Wikidata. This is essentially equivalent to Wikipedia, the entities that appear as entries on Wikipedia. Common sense relations between concepts from ConceptNet, and knowledge necessary to answer natural language questions in Squad. Squad is a popular question answering dataset, which is also from Wikipedia. Okay, so let's go over the knowledge sources. First, there's Google Re. This stands for relation extraction. And these are 60,000 facts manually extracted from Wikipedia. There are 5 relation types, but we only consider 3 out of the 5. Place of birth, date of birth, place of death. So this knowledge source is a little limited in the scope of what it'll query for. The other knowledge sources are much more diverse than this one. So the other 2 were excluded due mainly to multi-token objects. We'll talk about this later, but this is one of the limitations of this method, is that because when we query the language model with what is essentially a closed test with subject, relation, and masked object, well, from the perspective of modern language models, whether this is a single token or a multi-token word or phrase makes a very big difference in the difficulty of the task, in that they do much better predicting single tokens. So this is one of the limitations of this method, which arises directly from the limitation of the language models themselves, that they're not very good at predicting multi-token words or phrases. We'll see that this is also true for the other knowledge sources, but to query the language model efficiently, we need to build templates that make it natural for the language model to predict the answer token. So when we have a subject-object relation tuple, we will use a manually designed template to turn that into a natural sounding sentence. So, for example, for the relation place of birth, we can use the template or form subject was born in O, and this was born in was manually selected by the authors. And note that each fact in this dataset is by design manually aligned to a short piece of Wikipedia text supporting it. And this will come into play in one of the baselines that we'll compare to. Another similar but larger knowledge source is T-Rex. This is also a subset of Wikipedia triples, which deals with entities from Wikipedia. And this is much larger than Google Read with a broader set of relations. There are 41 Wikidata relations. Um, they subsample at most 1,000 facts per relation. The query templates are also manually designed for this knowledge source. For example, Francesco Bartolomeo Conti was born in. Um, Answer Florence, died in, born in. And in contrast to the previous one, T-Rex facts were automatically aligned to Wikipedia. And so there can be noise in this alignment, but other works have shown that you can get a very high accuracy alignment um, with uh, available alignment techniques. ConceptNet is a little different. This knowledge source is originally mined from a sentence corpus called OpenMind Common Sense, and this dataset focuses on testing for common sense knowledge. And by common sense knowledge, I mean things like uh, waking up in the morning is prerequisite of, where prerequisite of is a relation of eating breakfast, and eating breakfast is an effect of, where that's another relation of full stomach, and so on. The triples are extracted from facts from the English part of ConceptNet that have single token objects. We deal with 16 relations. And to create the templates for these, they chose to find the OMCS sentences that contain both the subject and the object. This makes sense because the triples themselves were originally extracted from these very sentences. So it makes sense to recover the relation from the original sentences. And so once you have that sentence, you can mask the object to get the query template. And if there are several sentences for a triple, they picked one at random. And for this knowledge source, there's no explicit alignment of facts to Wikipedia sentences. What is a popular question answering dataset? They took a subset of 305 context insensitive questions from the development set of Squad with single token answers, and they manually created closed style questions from the Squad questions. So this amounts to rewriting questions like who developed the theory of relativity to the theory of relativity was developed by and mask. Because Squad itself is created from Wikipedia, you also can get the corresponding fact for a question answer pair from Wikipedia. Okay, so the models that are tested are listed here. There's a separation here separating the unidirectional language models and the bidirectional language models. And the difference is that when you have a sentence, Dante was born in, I'll just reuse this example. The unidirectional language models process the sequence of tokens like this only in the forward direction, whereas bidirectional models also process them in the reverse direction. And so they just have a richer representation of the sentence. One thing we can notice that although these unidirectional models have more parameters, the corpus size is much bigger for the bidirectional models. So usually what this means is that the models that saw more data are going to be better, and this is borne out in the results as well. So I would say that comparing these two classes of models is not completely fair, but from the perspective of this work, it's still worth it to report results on this first class of models because they used to be very popular before the second type came along. And one difference between Elmo and BERT is that Elmo uses the standard language modeling objective of predicting sequences of tokens in both directions, whereas BERT doesn't actually do this. It doesn't actually predict a sequence of tokens. It just reads a sequence of tokens, and then it has a mask token that it tries to predict. And it does this using not an RNN like Elmo does, but using a transformer. So when you look at this masked language modeling objective, which is what it's called, it really is a closed task. So those are the language models that will be compared, but we also need non-language model baselines to compare to, and there are two baselines. One is a very simple frequency-based baseline, where for a subject and relation pair, the baseline just ranks words based on how frequently they appear as objects for the given relation. So for a SR pair, it'll just count the number of times that each object appeared as part of this SRO tuple. The second baseline, which is the stronger baseline, is the relation extraction pipeline baseline. And this uses a pre-trained relation extraction model from these authors. The relation extraction model is an LSTM based extractor, It's trained on a subcorpus of Wikipedia annotated with Wikipedia relations, and it uses an LSTM to extract relation triples from a given sentence. So I talked about how the Google Re and T-Rex datasets are aligned to some Wikipedia text or sentences. Well, that is used here to provide the relation extractor with the sentence known to express the facts. Since we have these original sentences at hand, we can feed the sentences to this relation extraction model, and then with the triples that the model returns, we can construct a knowledge graph. And at test time, we query this graph by finding the subject entity and then ranking all objects in the correct relation based on the confidence scores returned by the relation extraction model. So visually, the way this would work is for an identified subject, we'll find all of the objects that have some relation that we are looking for. Object 2, object 3. And we will just rank these objects by some confidence score that is returned by the RE relation extraction model. Now you might notice here that this baseline has the potential to be very sensitive to the model's ability to link entities, and since the naive version of the RE baseline uses exact string matching for entity linking, this can be problematic because, for example, for this sentence, the RE model extracted the subject Francesco relation born in, object Florence in 1681, but we queried it with Francesco Bartolomeo Conti, or born in, and wanted the answer Florence. Because the actual subject tokens do not match and the object tokens do not match, and this kind of token mismatch happens often in relation extraction models. So usually some entity linking solutions that can deal with this kind of token mismatch are employed, but because there is no such consideration here, the knowledge graph that we built with the relation extraction model would not be able to answer this query correctly, and that would lead the naive RE baseline to be very weak. So the authors also created the Oracle relation extraction baseline, which allows the model to essentially cheat and allows it to, as long as it predicts this relation exactly correct in that it predicts the exact tokens of the relation, they just allow it to look up the correct subject and object pairs from the original sentence that the relation was extracted from. So the relation extraction model could have extracted these slightly different tokens for the subject and object, but as long as it got the same relation tokens, they just allowed it to return these original tokens, which is why it's a little bit of cheating, but um, that's why it's called the oracle. And this allows the REO model to be much stronger. And it turns out that the best language model ends up being on par with this very strong oracle relation extraction model, which is the impressive part of the final results. For the results on Squad, they used the popular system for open domain question answering with a two-step pipeline called DRQA, Doctor QA. It consists of first stage where TF-IDF based information retrieval is used to find relevant articles from Wikipedia, and they take the top K articles that are retrieved and apply a neural reading comprehension model on it that extracts answers, and the predictions are constrained to single token answers. Before we look at the results, I'll go over just a few details about the evaluation. For metrics, they use a rank-based mean precision at k. So the value is 1 if the object is the object for an SR pair query is ranked among the top k results and 0 otherwise. And this is average over all relation types. In practice, they use the mean precision at 1, so this is essentially asking if the answer is top ranked or not. And finally, here are some considerations with the evaluation that are worth thinking about. One is that since we use manually defined templates to query the model with respect to a relation type, we can expect that the choice of templates has an impact on the results, and the authors argue that this means that the Llama probe measures a lower bound for what the language models know, meaning that if you're able to design better prompts or maybe automatic templates rather than manual templates that can probe the language model better, then you'll be able to elicit more information out of the language model. And in fact, there's at least one study, one follow-up study that does exactly this, and that study shows that you indeed can achieve better results by probing the model with a more diverse set of automatically generated query templates. Single token only. Yeah, only single token objects were considered as prediction targets, and this has had to do with the inherent limitation of language models in not being so good at generating multiple token phrases, and yep, multi-token decoding adds um, a large number of additional parameters, so it's hard to compare this across models. object slots only. We only query object slots and not subject or relation slots. They avoided the relation slots for two reasons. First, relations can span several tokens, which, as mentioned before, is a challenge for current language models. And secondly, regardless of that, relations can be generally expressed with many different wordings, which further complicates the evaluation procedure when you have different ways to say the same, express the same relation. And for subjects, by including reverse relations, you actually can query the subject slots. And finally, um, intersection of vocabularies. This is talking about the fact that each of the models that we consider are trained with different vocabulary sizes. For example, Elmo uses a list of 800,000 tokens, while BERT considers only 30,000 tokens. And since if a language model has a larger vocabulary, it has to distribute probability mass over a larger number of tokens. It'll be harder to rank the gold token at the top. For this reason, and to make it fair across all models, they only consider a common vocabulary of 21,000 case sensitive tokens that were common to all models. And every model and all of the model's predictions were restricted to only this set of joint tokens. We're now ready to go over the results. The main results are summarized in this table. It shows the mean precision at 1 that we discussed before. For the different models across the corpora considered. So these are the data sets, and the different models are here. The baselines are here. We can see that the base and large versions of BERT both outperform all other models by a very large margin. So if we look at these results, for Google Re, there's a very large gap between the BERT models and the other LMs. The same is true for T-Rex and ConceptNet. Comparing to the baselines, let's compare with the Oracle relation extraction baseline, which is the strongest competitor. And we can see that even with the help of the Oracle, the relation extraction baseline sometimes underperforms the BERT large model and is on par with BERT base. So the authors argue that this is an impressive performance given that REO gets the benefit of having an Oracle entity linker. One further note about the results on T-Rex is that there are different types of relations where it can be either one-to-one, n-to-one, or n-to-m. One-to-one relations are things like capital of, where there can be only one thing that corresponds to the thing being queried, whereas n to 1 is a case where many things can map to one, and N to M is many things mapping to many other things. So N to M is obviously the hardest case, and it's interesting that the relation extraction oracle performs best on this task, while BERT's performance decreases as this difficulty increases. So while BERT is very strong on what could be considered an easier task, we can see that there's there's still some room for improvement as the relations get more complex in the sense that there can be more ambiguity. Since not being able to rank an answer object as the top one retrieval candidate doesn't mean that the model necessarily doesn't know about the underlying object. They also show results with increasing values of k, which could be considered as the model has some knowledge of the object as it pertains to the subject and relation, but maybe not all of the knowledge that is necessary. And in this case, downstream models could utilize that knowledge. So this is still useful knowledge. This figure shows the mean p at k curves for increasing values of k. This scale is a log scale, and so k goes up to 100. We can see that the BERT models are also the best here as we increase the k value. And as we expect, the precision at k increases as we increase the k. So for BERT, the correct object is ranked among the top 10 in around 60% of the cases, and among the top 100 in 80% of the cases. So 60 and so this gives a pretty good sense that BERT has at least some knowledge of an object even if it's not precise. And from another perspective, combining this with the observation from before that BERT does very well on retrieving knowledge about one-to-one relationships, whereas it does less well on more difficult N-to-M relationships. We could make the case that the knowledge contained in BERT is somewhat more blended than the knowledge that we can extract with something like the RE pipeline or a standard knowledge base. So maybe that's one area of improvement in the future, making knowledge more explicit within BERT. In this next figure, we can see the Pearson correlation coefficient of precision at 1 with some other metrics. SM is the number of times a subject is mentioned in the BERT training corpus. OM is the same for objects. LPFP is the log probability score associated with the prediction, so it's BERT's confidence about its prediction. And we can see that the log probability of a prediction is strongly positively correlated with p at 1. So when BERT has a high confidence in its prediction, it is often correct. And that brings us to the end of the presentation. The takeaway is that a lot of knowledge is already baked into the weights of pre-trained language models, especially BERT models themselves. And this could be one reason why they perform so well on downstream tasks when fine-tuned. We also know that it's non-trivial to extract a knowledge base from text that performs on par to directly using the pre-trained BERT large models. And this is despite the fact that we have to use an entity linking oracle. So maybe it is possible at some point in the future that language models trained on more and more data with larger and larger models might one day become a suitable alternative to traditional knowledge bases. Some future works include quantifying the variance of recalling factual knowledge with respect to varying natural language templates and assessing multi-token answers. That concludes the presentation, and thank you for listening.